All right, so in this video, we're going to talk about the integral test. So we're going to use the integral test now from time to time to determine whether an infinite series converges or diverges. And so the integral test is stated as letting a sub n equal f of n be continuous, positive, and decreasing. And so these are the conditions that need to be met in order to proceed with the integral test. If those conditions are met, then the series a sub n and the improper integral either both converge or both diverge. So we can study the improper integral to determine whether or not the original infinite series converges or diverges. Now we'll take a look at a couple examples here, but one of the things I want to point out is this capital N right here. This is just some constant that's going to be defined within the function, defined within the series. Generally speaking, when we talk about convergence or divergence, as long as things eventually settle down as we approach infinity, then we're going to be okay. So many times this number is not as significant as it might have been in earlier sections. You'll see as we work a couple examples that I generally will use the starting index number for this lower bound on the integral. That being said, if we choose something different, many times it's not going to matter. So I've gone ahead and put an example up, and I wanted to keep the theorem here so it's easier for us to go back and talk about what it is we're doing. So in this particular problem, my a sub n would be 1 over n squared plus 1. And before I really do a whole lot, I need to make sure that I can use the integral test on a problem like this. Therefore, we need to make sure it's going to be continuous, positive, and decreasing. Now, the continuous part, you can just take a look at it as a function. You could see you would be continuous. Positive, remember if we have n being positive integers, plugging it into here, we shouldn't be any issue. We have an n squared, in fact, really no issues there. And then decreasing. You can see that if our n gets bigger and bigger and bigger, our denominator is going to get bigger and bigger and bigger, therefore it's going to be decreasing. So what I'll do next then is I'm going to go ahead now and consider, now that we have all three of these checked off, I'm going to consider the function f of x equals 1 over x squared plus 1. Okay, so now that's going to be the function that I'm now going to integrate as an improper integral. And as I mentioned before, I usually put the capital N value here as 0 if allowed. If you put it as a 5, it's not going to change the result of convergence versus divergence. And then we'll have our improper integral, again, approaching positive infinity, therefore needing that limit. So let me go ahead here and introduce the limit as t goes to positive infinity. Then we'll have our integral from 0 to t, 1 over x squared plus 1 dx. And so I'll go ahead now and integrate as usual. This is actually a direct integral. It's going to be our inverse tan. So we've got our inverse tan x evaluated from 0 to t. And in doing so, this is going to now be the limit as t approaches positive infinity, inverse tan of t minus inverse tan at 0. So in doing so, the inverse tan of t with t going to positive infinity gives us a pi over 2. Inverse tan to 0 is going to be 0. So this thing ends up equaling pi over 2. Now, remember what the theorem said. Let me scroll back up here. The theorem said that assuming the initial conditions were met, and they were continuous, were positive, were decreasing, then the series and the integral either both converge or diverge. Well, with us coming up with pi over 2, the integral converges to pi over 2, therefore, so I'll say as summary, therefore, the infinite series converges by the integral test. So again, since we hit a number here, therefore the infinite series is going to converge by the integral test. Now, I want to make a point. That doesn't mean that the series converges to pi over 2. Okay, the integral did, but the series does not. I actually punched this in a computer, and the series actually converges to pi over 2 hyperbolic cotangent of pi minus 1/2. And so I don't care about that number. We're not asking for that number. I just wanted to show you that it doesn't converge here. It's just saying that if this converges, then the infinite series converges. Okay, so we'll take a look at another example here. And in this particular case, our a sub n is going to be the natural log of n squared over n. The fact that we can pretty easily tell it it's going to be continuous. Remember, we're starting at 2, and so beyond it, we shouldn't run into any issues. We're going to be continuous. We're going to be positive. That's important to see. That's going to be positive. That's going to be positive. But then the decreasing isn't necessarily as obvious as it might have been in the last problem. So you have a couple of different things you can do. In an earlier video, I mentioned about when we talked about non-increasing and non-decreasing sequences. I talked about being able to create a ratio or even a difference and compare it with the inequality. And that's certainly an option for a problem like this. Another maybe more traditional way is if we move forward by saying consider f of x equaling natural log of x squared over x, we can find the derivative, set it equal to 0, solve it, and show that it's in fact decreasing like that. So if I go ahead and move forward with this derivative, this is going to give us a 2 minus the natural log of x squared over x squared. If I set it equal to 0, that's going to give me by multiplying this guy over, subtracting it around, that's going to give me a natural log x squared equals 2. Then at this point, I would probably just go ahead, bring the 2 down, divide it off to get a natural log of x equals 1. Therefore, x would equal e. So if I put this now on my number line, this being 2, remember that's where we're starting at 2, my e value would be over here. I don't really care about what happens over here because it's all about us approaching infinity. So if I take a number like 5 and I plug it back into this first derivative, you would find out that by plugging a 5 in, you would end up with a negative number. So that's just a nice way of, again, convincing yourself that you're safe to move forward using the integral test, knowing that it's going to be a decreasing function. Okay, so we've checked off all the boxes, being positive, continuous, and decreasing now. So now we're ready to move forward using the integral test with this function right here. So let me go ahead and slide this up. And I'll get it set up with a limit. So we're going to have the limit as t goes to positive infinity. Then we'll have the integral. I'll get to the bounds here in a second. And as I plug this in, this 2 that you guys see right here, I'm going to go ahead and bring that down. I'm just going to make things maybe a little bit easier to integrate with. So that's going to be a 2 natural log x over x dx. Now for the bounds. Clearly that's going to need to be a t on top as the limit goes to a positive infinity. On the bottom, pick any number that you want, right? Any number that's gonna work. Just don't want to pick something that's not going to work. Obviously want to pick something in the range that we care about. We specifically tested beyond e, and so e is approximately 2.71 something. So maybe I'll pick the number 3. It doesn't really matter, and you'll see that at the very end. When we take a number that's defined in our function, it should give us the same result. Okay, so I'll go ahead and integrate now. So u is going to be the natural log of x, du is going to be 1 over x dx, and I'm going to have the limit of the integral 2u du, which again I'm not putting those bounds on there yet because I've changed variables. But now as I integrate, this will just give us the natural log of x, quantity squared, evaluated from 3 to t. Okay, so I just added 1 and divided, coming up with this guy. Now, as I evaluate this, I'm going to have the natural log of t, quantity squared, minus the natural log of 3, quantity squared. And so as we approach infinity with our t, this guy right here is going to go off to infinity. So that's going to go off to infinity minus, and this is just some constant. And you can see if I would have put a 17 right there, this would have been the natural log of 17, would not have affected convergence or divergence. So it's perfectly reasonable to pick a number that's safe in the function and then to proceed forward. And in fact, you might be thinking, well, if it converges, would that matter? No, because we're not saying that it converges to that number like I pointed out in the last example. So this is going to be a positive infinity minus a constant. Therefore, our result is positive infinity. And per the theorem, if that happens, therefore, the infinite series that we started with, the natural log of x squared over x, diverges by the integral test. Diverges by the integral test. If the improper integral diverges, then the series also has to diverge.